Okay, good morning, everybody. Good evening to Dr. Tri Laksmana Astra Atmaja. It's nice to meet you again here. You will give a lecture, continuation from the yesterday lecture, right?
Yes.
Okay. Thank you. So if someone want to ask a question to you, is it okay directly, or we wait until the end of the session?
Just put it in the chat. If you can also interrupt. I'm not sure if you like. Just
okay.
Just don't be shy. You can also interrupt.
Okay.
Put in the chat. So Pakun, you can also interrupt me if you see something in the chat, because I don't always look.
Okay. So anybody who wants to say some questions, yeah, you can write the questions in the chat room, or you can also raise your hand. Yeah. Well, Dr. Tri Laksmana, it is time is yours.
Okay. Thank you. And hello again, everybody. It's good to see you again. So now we'll continue our discussion about Bayesian inference. But before, I have to excuse. You have to excuse me. I have to take my mouse. I forgot to pick it up with me. Sorry, excuse me. I'm using a laptop, and this mouse is terrible at the point. So. Okay, now. Slide again. There it is. And okay, so now can you see the screen? Okay. If I move the screen, do you see the screen move? That's also important. So we're in slide 2.
Yeah, it's okay. It's good.
Okay. All right. So that's good. I had sorry about yesterday. So yeah. So hello again, everybody, and thank you. So today we're going to continue Bayesian inference. So we're going to continue the logic that we already outlined in the last couple of days, and also going to build on Professor Feigelson's lecture this earlier today. So we have just a little bit of a short review. We have actually seen Bayesian theorem before in the last couple of hours. In fact, we already sort of seen it when we talk about probability. So they already has been named. So they already has name. This is the posterior, and that's the likelihood, and this is the prior, and this is what we call the evidence. But actually, this is just a normalization constant. If you look at the fact that a PDF has to be normalized, right? So that's this is its definition. So yeah, so basically, Bayesian theorem is a codification about what we think our data, not only our data behave, but about our what we think about the origin of our data, where it came from, what sort of model generates it. So that's the basic idea. So we're not going to talk much about the derivation. It's already been discussed before, but rather I'm going to show you several examples, just to get a feel of how are we doing inference in a Bayesian way. Right? Some of these are going to be just simple problems, toy models. Don't be afraid of toy models. or don't look down on toy models. They're actually quite nice tool. Later on, we're going to talk about we're going to discuss about how are we doing Bayesian inference in astronomical research. That's what we're going to do toward the end. So let's on to the first problem here. So this is called the lighthouse problem. It's from this book. It's a really great book. Highly recommend to read it. So basically, it goes like this. It's a really simple assumption. There's a lighthouse. We don't know where it is, but we know the lighthouse is beaming light at random interval. We don't know when. And then along the detector, along the shore, along the shore, there is a detector that detects the flash of light. The detector, however, only detects the fact that there is a flash. It doesn't record the direction. It doesn't record anything. It's only record the fact that it detects a flash at this position. All right. So then perhaps the detector is placed everywhere along the shore, or maybe it's put in a different place each time. So anyway, it records the flashes of light hitting random places on the shore. So that's the data. So if we have n flashes, then we can ask, where is the lighthouse? That's an inference problem, right? Because we don't know alpha, which is the position of the lighthouse perpendicular to the shore, and we don't know beta, how far it is out to sea. So we want to infer this position of the lighthouse. So let's look at the situation here. The lighthouse emit flash of light at random time. So that means it's rotating, and then at random angle it emits light, and then the lights go straight away, and then it's recorded by a detector along the shore. So then we can assume that it's randomly. So the angle is randomly distributed uniformly. This is what we call a uniform distribution. But however, because we see the flash on the shore, so it must only lie between 90 degrees and minus 90 degrees. So if it's here, we can't see it. So that's why the prior we impose, although it's uniform prior, but we impose a limit. It must only lie between minus 90 degrees and plus 90 degrees. Right? Okay, so just use simple trigonometry. If you know if there's an angle, there's this distance, then we can use this. Now we can change this distribution, p theta, distribution of angle. We can transform it into a distribution of position, right, by means of change variable. So the probability of finding an angle multiplied by the first derivative, this term here. So here is the derivation of both sides of this equation. So we get this. So then we have this, and so forth. And then remember the relations of this simple trigonometric relation. So we have this, right? So we have the expression that we got. What is the probability of observing, detecting a light at this position, given that the position of the lighthouse is at alpha and beta? That's the expression. Now it doesn't look like Gaussian, but nevertheless, this is our likelihood of observing a flash at position xk. So now let's think about the prior. So now we have two parameters. Before that, as usual, we have to think about what is the probability of detecting all data set. It's this one. Just the usual. It's just the product. Now the prior. That's the prior, and that's our expression of the posterior. I just uploaded the slides few minutes ago. So if you haven't downloaded, I apologize for that. I hope it'll get distributed soon. So now we have to think about our prior. So, well, yeah, I know there's a lot of bashing in uniform prior in the last few hours, but come on, it's not a bad prior, honestly, if it's used properly. So now let's assume uniform prior, and then we limit this between, the shore doesn't go all the way, right? There must be some certain distance over there and over there. You can set it up as long as the Earth's diameter. That's fine. But in the end, we'll see that if we have a lot of data, this one will matter. How far do we want to go, right? But yeah, come on, we don't know anything about the lighthouse, so let's just use the most simple prior. Now, let's assume that we know how far the lighthouse is from the sea. It's beta. Let's assume we know it. Let's say, I don't know, 1 kilometers. So we can drop off the term. So now I'm going to run a simulation. So I'll share the code after. We generate a random angle between 90 degrees to plus 90 degrees. And we simulate the detection just with this. So now we have a sample of locations of where we detect flashes of lights. Now, of course, we don't know these values, right? But the computer knows. It just doesn't tell us. That's our task to infer these values, right? So computer. So for now, only the computer knows. So what we only have is XK here, this set of data that we record where it tells us the positions of where we record the lights, right? So we have a set of data, right? So then we can actually see what the posterior looks like. This is just univariate, so it's just to calculate the posterior. It's just simple. Just set up a grid of alpha between certain range, and then just calculate the posterior. We already write it down, right? All of these terms. So this is for the posterior when we only have one data point. Look at that. We record a flash here at, what is this? About 3 kilometers, right? Then from our reference point. And because we only have one data point, so it just assume that the lighthouse is just in front of that, just in front of this position. So the highest probability is the point. However, when we take a second data, there's this it records here. So then the PDF, the posterior, it becomes bimodal. So it records two peaks. It says the most probable value of where the location of the lighthouse along the shore is either here or this. Which one do we want to pick? Well, we can pick whatever it is. But say that we take more data, then apparently the third data happen to be here. Then the second peak collapse. It's still here though, but it's very weak now because now we have what, 2 points here, and so forth. So the more we collect data, so look at this. This is called a rug plot, if you remember. So the more we collect data, the more we can determine the horizontal location of the lighthouse. So that's how we do inference. So the posterior tells us it's a combination about what we know based on the data and what we know based on our assumptions. If you don't have a lot of data, the shape of the posterior will very much depends on the prior. So that's the takeaway from this exercise. So now we want to do multivariate inference, right? Before we assume we don't know beta, but now we assume we don't know. We don't know it. So we want to infer them both. So now the posterior, it's a joint probability. What is the likelihood of alpha and beta together? same likelihood, but now we have to include the posterior for beta. So what's the appropriate prior? Yeah, come on, we don't know anything about it, right? If you want, we can think about any other prior, like, you know, horizon distance, you know, anything. But then we have to infer the height of the lighthouse. But seriously, that means now we have one more variable to think about. You see, this is the problem. The more we add, the more we think about an informative prior, the more that we think that this some more variables we have to include, and then we have to think about whether we know anything about this new variable or whether we have to infer it together. So if we just use non-informative prior, then we might still get something out of it. So, but don't worry, this is almost the last time you're going to see uniform priors in this presentations. So we'll try a different one next time if it's you know, if it's warranted. Right. So now we do the same exercise, but now we calculate the posterior in 2D. So this is the grid of alpha and beta, and this is when we have 1 point, and we have the 2 point. Remember, we have 2 peaks. Now we have bananas, right? This yellow thing. This is the area where the lighthouse might be located according to the posterior and the data. We have 2 points here. We have 2 points here. Who knows? Maybe it's around here. But as we have more data, 3, 4, and so forth, we're pretty much certain that the lighthouse is here. So we can see here that the PDF, the posterior, it's only 1 peak, and the peak is very small, which means that it can be determined with nice accuracy. You can see here we start to have some idea about where the posterior is located at when we have about eight measurements here, as you can see. Right, so we have seen this likelihood. You know, if you think it's funky looking, it's because it's not a Gaussian. It's called a Cauchy distribution. We'll encounter it several times probably during this whole virtual course. So the black one, that's what the Cauchy distribution looks like in 1 dimension. It's like a Gaussian. It's centered around a mean. It's not actually a mean. It's centered on center point, and it also has a width, the full width at half maximum. I hope you're familiar with the term. That is the width at half of the peak, half length of the peak of the PDF. That's about 2 gamma. This guy here, and if we compare it to a Gaussian distribution shown here in orange, the Cauchy have a wider tail here. Right, so that's why people sometimes use Cauchy as a likelihood function, because it has a wider tail. It's more robust to outliers. We'll discuss about this later tomorrow when we use this to have a more robust outlier. So Cauchy distribution is quite useful one. Right. So that's how we do inference. We're going to talk a little bit more about inference after this, but now let's talk about hypothesis testing. So now, are you already familiar with this problem? So now we have a data set, and we have a set of models that we think we can describe the data. What is the correct model? So basically, what we want is we want to know the posterior of the model given the data. And if you use Bayes' theorem, it's this expression that we need to solve. And we know it that this guy here, the bottom part of the equation, the denominator, that's a normalization constant. It is basically a summation of the numerator for all possible models that we want to evaluate. So then the posterior for the K model is this expression here. It's just weighted by the sum of the numerator here. Okay, now just to make things easier, let's look at how what is the expression for when we only have two models. Let's say we have two models, M0 or M0 and M1. So that's the expression of this expression from these equations. And if we divide this whole thing by this, we have this, and we have, and R here is the posterior odds ratio. So this is usually what we want. We want to get this number to see how significant is, how better is the model M0 to M1. Yeah, so then if you want to have the posterior probability of M0, then we need to have these three quantities. So for example, what I want to discuss is this prior probability for the model. This tells how probable a model is. If we favor a certain model, then by all means put it in the express it in the prior. For example, we're doing testing, for a patient, whether the patient has a disease or not. So now we can look at the profile of the patient, and we can calculate how what is the probability that the patient might have this disease. So that's our prior. But however, if we have no information, and we can say that M0 and M1 are equally probable to be true. So then this gives us only this. That's this is what we call a Bayes factor. So this is just the ratio between these two probabilities. So it's so if M0 is higher, then the Bayes ratio will get large. That means M0 is more significant than M1. So how significant is it? There are various ways to do it, but here's a paper by Carson Raftery in 1995. They give a table. If you just take the log of Bayes factor, so if it's more than 2, then M0 is decisively more correct, more significant than M1. Between 1 and 2, it's strong, and so forth. You can look at this to evaluate. So now here's a example problem. So, that just to illustrate how to do it. So here's an example problem from this book, Practical Bayesian Inference. Also, again, this is a very good book, and I highly recommend that you read it. And maybe just some disclaimer that I work with Basil Jones for quite a number of years. So that's why I like the book. But honestly, he's also a good writer. So yeah, so there's a test for breast cancer. It's 90% reliable, which means that if somebody has breast cancer and got tested, the test will come out positive with a probability of 90%. Now there is, however, the probability of testing positive when a patient actually doesn't have the disease. It's 7%. Now among women between 40 and 50 with no symptoms, 8 in 10 will have breast cancer. Now there is a woman, she's 40 something, and she tests positive. So what is the probability that she has breast cancer? Now let's take a short break, maybe a couple of minutes, and think about this. I need to. You have to excuse me again. I have to do something. So have a look at this and think about how you can answer this, and I'll come back to ask you.
Okay, thank you, Dr. Laksmana. So
yes.
Okay, if you want to have a break, please.
Yeah,
But
something
if
like that. So
someone wants to say some question, please type in the chat room.
oh yeah, no. I'll be back. All right. Does anybody has a question?
So it is still no question until now, I
No
guess.
questions? Okay. Does anybody know how to answer this?
Okay, Abdullah.
Okay. Yeah, Abdullah, what do you think?
Yeah. So should we multiply the 40 something with 0.9? So this is the probability that she has a breast cancer, right?
Yeah. So 0.9 multiplied by
40. So it's gonna be 36 something, right?
well, 40 is the age. So it's not a number.
I'm
So it
sorry.
says that
And then yeah, we multiply it by 8, which is the 8 women's, right? Or not?
yeah, so 8 in 1,000 women age 40 and 50 have breast cancer. So that's information.
Oh, okay. So
So what do you think?
So 8 in 1,000 is the prior, right?
Yes. No. 8 in 1,000 is the prior that you have breast cancer. If you're a woman between 40 and 50. All right. Let's move ahead. Right. So we need to parse the information and understand what's all of the numbers mean. So let's say the data is D, and M0 is the hypothesis that the woman has cancer, and M1 is the hypothesis that doesn't have cancer. So before, it's the test, it will be positive when she has cancer with 90% reliability. That means the probability to have positive results given that she has cancer is 0.9. Now the probability that the test will be positive when she does not in fact have cancer is 7%. It's false positive rate. Yes, Abdullah.
oh, I'm sorry, I just forget the raise hand.
Okay, no problem. Sorry. Yeah, so these are two different values. It's called a true positive, and this one is false positive. True positive mean it's you get positive results when you're actually when the hypothesis is actually true, and a false positive is, as you guess it, it's what if you get positive results when the hypothesis is actually wrong? When you so you can get tested and then it came out positive, and then turns out you don't have the disease at all. It's just it's just a flaw in the way we test. And I think by this by this point in the pandemic, we're already quite familiar with this term, right? With false positive and this and that. There's a lot of tests there to see whether you have COVID or not, and there's always this thing called false positive rate. What is the probability that you're positive, but actually you're not? This has gained quite a lot of discussion among people these days, right? And now we have a prior, right? You're correct. It's 8/1000 is the probability that a woman in her demographic has cancer. So because this is mutually exclusive and exhaustive, it means the probability that this woman don't have cancer is actually quite high. It's 99.2%. So now we all have all informations together. So if we put this into the equations, then you get a number. It's a little bit less than 10%, 0.094. That means if you're a woman of 40 and you do a breast cancer test and it came out positive, there's only about 10%. I mean, according to this number, that 10% chances you actually have cancer. I mean, isn't this scary? I mean, we did a test and then it came out positive, and then we got, oh my God, I got cancer. You know, a lot of worries. So what's going on here? I mean, the test is supposed to be like 90% reliable, and you know, but why is it actually it only has about 10% chance that we actually have the disease when it came out positive? So there are two reasons for this. First, if we look at the prior, according to the data, it's actually quite rare that you're going to have cancer, unless if you don't have symptoms. Like it's only 8 in 10. So in the first place, there's already quite a high possibility that you don't actually have cancer. And secondly, the false positive rate is apparently quite high. It might look low. It's only 7%, but there's actually a high probability that you don't have the disease in the first place. There's 99.2% that you don't actually have the disease. So that's a problem with this method of testing if the numbers are true. Yeah. So here's some illustration again. So what should we do with this fact? So what if we increase the reliance of the test? So this is PDM naught. Once again, this is the probability that you're going to get to be this probability that the test is going to be positive if you have cancer, and the line and it's over here, right? And this is the probability that you'll get cancer, that you actually have cancer if the test is positive, right? So this is 90% reliability that we have seen. Yeah, as we have seen, the probability is only about 9%. So let's say we increase it to 95% or even 100. As you can see, it's only increased almost linearly. So even if the test is 100% reliable, that it will always show positive 100% of the time. So it doesn't really mean that we're going to get cancer. Actually, the probability is only 10%. Only slightly higher than if the test is 90% reliable. So why is that? Because the probability that you actually have cancer, I mean, no, sorry, not you. The probability that this woman who is in her 40s, show no symptoms, to have cancer is actually very low. It's only 1 in 8 in 1,000. So this is the line, and this is the false positive rate. And this axis here is the same as this. This is the probability that you'll have cancer if the test shows positive. So as you can see, the false positive rate that we have 7% is around here. So that's why the test. So that's why the probability that you actually have cancer is quite low. If we improve the test so that it lower the false positive rate to be below 8 in 1,000, which is the baseline, then we'll show marked improvement. So if the false positive rate is like 1 in 10,000, then it's almost 100% here. So So suppose you have a test. I don't know what kind of test is this. You know, MLI or and blood test, whatever. Let's say it has 1/10,000 false positive rate. Then and then we do test, then it shows that you're positive, and yeah, you have to worry because you have cancer. But if the test is shown to be only 10% or less, and the disease is already quite rare, then yeah, we probably don't have to worry too much. Either we find a better test, or we take a second opinion or whatever to actually make sure whether we actually have the disease. So that's the problem with very low number. If the baseline, which is the disease that we're testing, is already quite low, there's a lot of rare disease out there, and it's already quite low, and the false positive rate has to be also quite low, in order to make sure that we actually have the disease. So let this probably if this is new to you, then I hope this makes you aware about this whole probability statement, as about what it means, and then next time if you think you have a disease and you want to take a test, look at the false positive rate. That's the most important thing. What's the probability that it'll come out positive even if you don't have a disease? And the second thing is look at how rare or how often the disease is. So that's hypothesis testing in a simple way. Right. And now we're going to talk about coin tossing. It's another simple problem. So you have coin, we flip a coin. There's always a chance, 50% chance that it will appear heads. Right? Coins has two sides, heads or tails. I mean coins everywhere are different. But this is a very American thing to call coins heads or tails. So let's say we throw a coin 4 times, and then 3 times heads came up. Is there some funny business, or it's just probability? If you toss a coin 10 times and then heads came out 8 times, is this normal for a coin to behave, or there's some funky stuff with the coin? Maybe it's a gambler's coin. So now that we have the problem, we set up an experiment with this coin. So we throw the coin n times, and then we count how many heads that came up are. So now we compare two hypotheses or 2 models. That this coin tends to have a fixed probability for heads to appear, right? Pi. So this number we can set up. Let's say if we set to a high number like 0.9, then we say that this coin tends to be more towards heads to appear. And then the second hypothesis is this is just a normal coin, but we just don't know what's P. So what is likelihood model here? So we can use binomial distribution. A binomial distribution, it describes the probability of how many times you'll get an event R after n experiments. After n experiments, when we know the probability of R to occur is P. So here are several examples of binomial distribution for various cases here, but they all have the same. And in this example, we just set up that the number of experiments is 40. But we change the probability. So if we set up 40 experiments and we know the probability is 0.1, then the peak the most likely number of success to come out is 4. Yeah, 4 times 10%. That's 4, right? But it's also likely that if we do 40 toss of coins and actually you won't get any heads. That's possible, but it's very unlikely. Even more unlikely if it's after 15 coins there's no heads. After 50 throws, you only get 15 heads. That's unlikely that you have a lot of heads when the probability is this much. But if the coin is like 50-50, or not coins, events. If the event is 50-50 here, and the most likely number is you'll get 20 success. But it's also possible that we'll get only like 15 success, or even more, 25. So yeah, so this is a description of how many success that can possibly occur if we know what's the probability of success. Right. So in order to calculate the evidence, we have to integrate out the parameters here. This is the definition of the evidence as a normalization constant. That means we have to think about the prior for both models. For M0, we define this as a delta function. So the prior for P is just a single point. All of those are 0. That's a delta function. It's only 1 when P is 5. The number that we set up, and all of those are 0. So obviously, if we integrate the P, then we get this 5. Then we get 5. So it's a binomial. So it's a binomial distribution. So the evidence for this is a binomial distribution. But the probability is 5. Set up. Now the other one is quite complicated, because if we don't know anything about P, then what? Do you want to use uniform prior between 0 and 1? Yeah, you can do that, but come on, we know a function, we know prior that can describe probabilities. A PDF in P. It's called a beta distribution. We'll use this tomorrow, for MCMC. Right? And, okay, it's like a binomial distribution, but you have a bunch more parameter, and then you have this B. It's a beta function. So there's beta distribution, this guy here, and there's a beta function. That's 2 different things, but they're related. And you have the scary integral, and you have the scary exclamation points here. There's a lot of screaming in this function, but that's what a beta function looks like. Now, a beta function is defined just like a Gaussian is described by mean and standard deviation. Beta function is described by A and B, the choice of A and B, or alpha and beta. I'm sorry, I write down alpha and beta here, but I write down A and B. It's actually alpha and beta. So sorry, but anyway, depending on the setup of the prior, we'll have a different beta functions. So there's beta functions that skew toward the low probability, like the green one here. There's one that skew toward high probability, like this red guy here. There's one that looks like a Gaussian around 50%, like this purple guy here. There's this one that's uniform in the center but very skewed on the edges, like here. And also, if we take 1 and 1, then we have uniform probability between 0 and 1. So yeah, uniform probability is everywhere. Even in a PDF, in a prior distribution like this, depending on how we set up. Yeah, so then we can calculate the evidence for this guy. Now there's some scary integrals, but look, even though this looks scary, this is actually a beta function. Again, but with different terms, right? So this is what it looks like. So this is the expression for the second model, where we don't know the prior, where we don't know the probability. So now we have the expression of the evidence for both. So we can calculate the base factor. We can assume that the model are equally likely. So then we use the base factor. It's become this. So we can calculate. So we're lucky here because we can actually have an analytical expression for the base factor. This doesn't actually happen very often. So if we do n experiment, and then turns out if we do n coin throws, and then we do and then we get R heads, then we can calculate what is the probability that the model that the coin has this pi probability it's going to be in terms, and we can evaluate it in terms of base factor. So let's do that. So now we toss n coins, then we observe 4, and we observe R came out heads. What is the likelihood that the coin has p equals 0 equals pi? I said pi here 50-50, 50%. So it's basically we're asking what is the probability that the coin is fair? What is the probability that the coin is fair? Right. So if we do only 5 throws, and then we see 2 heads or 3 heads, then there is no evidence that the coin is fair. I mean seriously, we only take 5 throws. Even if we record 4 throws, or even if we record 5 heads or 0 heads, it's not really an evidence that the coin is unfair. Now, if we have more data, so now we have 10 throws, and if we get 10 heads, 0 heads, it's still not a substantial evidence that the coin is fair. The coin is not fair. If we have 5, it's not even a evidence that it's fair. So as we take more data, then depending on how many heads we get, then we'll start to see very strong evidence that this is a fair coin. So if we throw if we throw 100 times, like this one here, and we get 50 heads, then there's a substantial evidence that the coin is fair. If we throw 100 coins, if we throw 100 coins and we get 25 heads, there is no evidence that the coin is fair. This is what it tells you. So you can see here there is a range here in which how many throws that we can have indications that a coin is fair. So if it's more than 60 here probably, or less than 30, that you get heads or not, then that's an evidence that this is not a fair coin. So that's the idea. Here again, it's a codification of our data. How many data do we take? What's the quality? And about our priors. And here we use beta priors. Now here the parameter is only one-dimensional. What if we have more parameters? So then we have to integrate out here, and we have done the integration for one parameter. But what if we have 2? And what if the data is and what if the prior is complicated? Then we have to do it numerically. We cannot do analytical integration in high dimensions. It's going to take very longer than the age of the universe to solve. This is called a curse of dimensionality. So we have to do numerical methods to sample the posterior here and then solve the integral. There are several ways to do it. In the Monte Carlo sampling in high dimensions, we're going to talk about it tomorrow, or Laplace approximations. That's another method, which is simplification. We assume that the posterior is a Gaussian, and a Gaussian is very easy to integrate. Now I'm going to talk about how we do inference with astronomical data, namely to estimate distance from parallax. So, but before we go on, is there any question?
So, any question? We can write your question in the chat room. It seems no other questions.
All right. Then,
Maybe you can continue.
Oh yeah, there was an answer. Fisak, you're right. Yeah, I'm sorry, I didn't see. I didn't see in the. I didn't see him. I didn't see in the chat room. Yes, so that's the right answer. 9%. You know, for the evidence for breast cancer. Well done. Right. How do we get distance from parallax? Right. We learn in school. You can just flip them. Right. 1/, parallax is distance. Right. It's common knowledge. Now, unfortunately, this is wrong. Yeah, even though it's taught in schools, in universities. Why is that wrong? First, what if you have negative parallax? Right? If a parallax has to be negative, has to be positive because distance has to be positive. But if you have, if you look at catalog, stellar catalog, you'll encounter negative parallax. So how do we get the distance, right? So we can do negative parallax when we flip the parallax. And the second thing, only when there is no noise, there is no measurement uncertainties that we can flip the parallax. But we don't live in a universe with no noise. We live in a universe with noise, as we have discussed many times also in this virtual course. So we have to deal with estimating distance in the presence of noise. Now, speaking of negative parallax, and a lot of people, when compiling samples from an astrometric catalog, they usually just ignore negative parallax, right? Okay, here's my selection from a Gaia catalog, for example. I'll get rid of the negative parallax, and then I'll only take stars with relative errors of less than 20% or 10%. So here's terms that we're going to use very often. It's the relative error. This measurement uncertainties divided by the parallax, f-ops. So usually you'll read this many times in astronomical journals when people are analyzing. Okay, we collect a sample of stars from the Gaia catalog. We only want the good ones, and yeah, so we reject stars that are negative parallax, and we only take 10%. Now look at this is from 5 years ago, but this is still this is from 2016. This is from an simulated astrometric catalog. It looks like Gaia back then. We still don't have Gaia, and this is the distribution of f-ops. Yeah, and this is the cumulative distributive function of f-ops. As you can see, almost 20% of Gaia stars will have a negative parallax. So it's quite large. Why? Because Gaia is going to observe the whole sky. It's going to observe a billion stars. Most of them are going to be very faint. So most of them will have poorly measured parallax. Hence, the parallax is negative. And 20%, almost 20% of them will be like that. And if you only take 10%, if you only take stars that are have relative errors of 10%, it's going to be between this and these two lines here. So we are wasting a very large part of the data. We're throwing away a large fraction of the data. Most of stars in Gaia will not have 10% parallax error, or even 20%. It's only going to be 20% of the catalog, or maybe even 10%. So we're going to throw away 80% of the data that has been taken by satellites, very expensive satellite, and it's paid by taxpayers of Europe to the astronomical community. So don't do that. That's what I want to say. And then this is a bit of explanation about the likelihood. So we do measurements with Gaia, right? And then we measure parallax. Now the probability that we'll observe this parallax will depend on the inverse of the true distance that we don't know, right? So if we draw the likelihood in terms of parallax here, then we get a nice Gaussian. This also explains why we have negative parallax, because if the star is very far away, if we flip to get the true parallax, it'll be very close to 0. But because it has measurement errors, then there's a chance that the observed parallax will actually be here, and it's negative. What do we mean by negative parallax? It means that when we're solving for the astrometric motion, we have to flip the orbit of the Earth. That's unphysical. That's true. But negative parallax means that the star is very far away, and the measurements is poor. That's information. Yeah. When you have negative parallax, it's not bad data. It's actually information. It tells us that the star is very far away. That's why it got negative parallax. Now, if we transform this likelihood and then we draw this in terms of distance, we'll see a tail here. Yeah. So if we draw a star and it has 20% relative parallax error, and we draw the likelihood as a function of distance, we'll see a tail here. So the uncertainties here is longer than the uncertainties towards the shorter distance. Of course, the peak, the mode, is still 1 over observed parallax. Now, if suppose that the star is very badly measured, yeah, we have errors of 50%. So the tail is extended, and the uncertainties here is infinity. So that's an illustration of why flipping the parallax is a poor practice. So how we do that? We have to see distance estimation or distance inference as a Bayesian problem. Yeah. So we want to get this, the probability of getting distance, given that we observe its parallax and its measurement uncertainty, is going to be the likelihood times the prior. And we have seen the likelihood, it's Gaussian, it's centered around 1 over R. So as you can see, this linear transformation becomes the problem. So this is our probability of observing a star with this parallax, given that the distance is 1 over R. Given that its distance is R and its true parallax is 1 over R. Now, what sort of prior we use? So let's have a look at three kind of priors that we can think about in this we're facing the situation. First, yeah, you guess it, uniform distance. It's everywhere. In fact, we're going to use this because so that we can see that this is a bad prior that we shouldn't use for this kind of situation, right? It has to be, this is an improper prior, as we have known, so we have to limit it between 0. Yeah, stars don't go, distance is not negative, and we have to limit it to a certain distance, like limiting distance, right? This is what it looks like. This is what the posterior looks like. For example, we have a star at we observe it at 1 milliarcsecond. We observe the parallax to be 1 milliarcsecond, and then we set up this limiting distance to be 100 kiloparsec, which is, it covers the whole galaxy. So I think it's very rare that the star is going to be this far that can be observed by Gaia. So when the relative error is quite small, like 10%, it behaves nicely, right? It looks like Gaussian. But as we have seen, it's 20%. It starts to show a tail. 30%. The tail at the farther distance got extended. Remember, this is in a log scale, yeah. So the uncertainties goes to 10 kiloparsec, which is bad. If the star is poorly measured, like 50% relative error, then the tail goes all the way to the limiting distance that we set up. And if it's 100% relative error, it looks terrible. It's a poor estimate of the distance. So if we calculate the mode, we get the mode is 1 over parallax. So from a Bayesian perspective, when we flip the parallax, we're actually assuming that stars is in a uniform distance. It can be at any distance, which is not true for a star. Yeah, we know stars are not uniformly distributed in distance. It's not even uniformly distributed in space. Yeah, we know that the stars in the galaxy is distributed like a disk. So in one direction you'll see more stars than in one direction in the disk you'll see more stars than we'll see stars above the plane. So this is obviously not a good prior. So one prior that we can think of is what we call an exponentially decreasing space density prior. So we assume that the stars, they are distributed in a space that's in a density that's exponentially decreasing from us. Yeah, so that's why there's this exponential term. But the rate of exponential decrease is scaled by the scaling L. Now, so we assume that in all directions, regardless of whether we are looking towards the galaxy or looking toward the away from the galactic plane, this is our prior. Its volume density is decreasing exponentially according to the scaling. So this is what the prior would look like if the scaling is 10 kiloparsec. And again, we'll show the posterior again. When the prior is 10 kiloparsecs, yeah, and if the relative error is 10%, this is what the posterior PDF looks like. It's nice. So we have, if it's 20%, it looks like this. And look, when it's 30%, there's a hump here because the posterior starts to consider the peak of the prior, because the data is poorly measured, yeah, because the error is 30%. It starts to consider another possibility beyond this peak. Perhaps because of the uncertainty, is it possible that actually the star is actually here? So then, when it starts to increase, then the peak then the hump starts to become a peak, becomes more prominent, and then starts to take over. This is what we call, we can see here a nice, we can see a transition from data driven to prior dependent. Yeah, so when the, so when the data is good, the posterior is dominated by the data. But when the data is bad, it starts to rely more on the prior. So then it starts to be more prior dominated. And in between, there's a transition here, depending on the measurement uncertainties. Yeah, and when the data is terrible, it starts to become the prior. We'll see that this is not really a problem, so, especially given that the data is already quite bad. Now another third prior that we can also use is a highly informative prior that use a galaxy model. So we know how the galaxy looks like. It looks like a disk. So we can set up a prior where it's dependent on the direction where we're seeing. So we have a joint prior here. It tells what is the probability of getting a star at this distance and this direction. L and B is the galactic coordinate. So the volume, the density of stars will depend on the mass model of the Milky Way here, and the mass model will depend on where we look to and how far it is. But Gaia cannot see all stars, right? So a satellite, we cannot see all stars in this direction. So this because some stars are just too faint to be detected. So we're probably only going to see the brightest stars. But so we have to know. We have to model the selection effect of our observations. For that, we're going to need a luminosity function here, pi mg. Right? So we have to integrate the luminosity function, because the luminosity function tells us the probability of finding a star with this absolute magnitude. Right? So we have to integrate this along the line of sight, to get an estimate about how many stars we're going to see. So we have to integrate from the brightest end of the detector to the faint end of the detector. So it's just a model. It's just a distance modulus. Yeah, this is the limiting magnitude of the instrument. I'm using Gaia magnitude because back then we were working on this to prepare for Gaia. But then what we are going to observe, the absolute magnitude, and what we are going to observe, it's going to be dependent also on the extinction. So we have to think about extinction as well. So we must, so in addition to Milky Way mass model, we also must have luminosity function, and we also have to have extinction model. So yeah, so that's the model. So that's the model for the Milky Way. That's the mass model of the Milky Way that we're using. That's the probability to observe a star at various direction. But this is the on average, the probability to observe a star decrease. This is the integration. This is this integration term here, and using this, and we get this, and then we get this line here. It tells us that the further we are seeing, the less star we are seeing. So most stars that we are seeing is actually close by. Right. This is what it looks like when we're this is for the posterior. I'm going to show you what the posterior looks like when we're looking towards the galaxy, the center of the galaxy at L0 B0. This is the green is again the shape of the posterior. Sorry, the shape of the prior as shown here. We see here a really crazy narrow peak. This is the galactic center. We model it as about 8.5 kiloparsec. This is the bulk of the disk. So most stars, when we're looking towards the galactic center, exactly towards the galactic center, most stars will be disk stars, but a high number of stars will be in the galactic center because of high density. Again, the prior looks nice. If it's the posterior looks nice. If it's the error is 10%. And when it goes to 30%, it starts to consider that the stars might actually lie in the galactic center. And again, and when the star is really bad, when the measurement is really bad, then it's like this one, it starts to become the prior. Now, what happens if we apply this to stars with here in the previous example, the star is measured to have 1 milliarcsecond parallax. What if we have the opposite? we measure the parallax to be -1. Then the star will have at this relative error, then the star is assumed to be very far away. It should be located in the galactic center. So this works for negative parallax. Now I'm going to show what the posterior looks like at several directions. So we have seen this curve before for the galactic center, and this is the posterior at several directions. Greens are once again the prior, and black is the posterior. So the black is for 50% observing relative error, and reds are for minus 25% relative error. So as you can see here, if we look away from the disk, like here, and then we have stars that measure to have negative parallax, then it highly assumes that the star is halo stars, right? So which is probably not the wrong answer, given that the parallax is negative. It might possibly be it. All right, so let's try how good the prior is. What is the performance of all these three priors, to a simulated catalog? So we use a GAMS. We can use a GAMS catalog. It's a synthetic Gaia catalog. I probably just need to give you a warning that we use the old version of the catalog, so because this was we were working on this a long time ago. This is the parallax error model. This is how the uncertainties are distributed along the true distance. So this is fake data, but you can see the line, and it's if you want to know the true relative error, it goes toward this. It goes bad toward this. So now to summarize the performance, we calculate the bias, the standard deviation, and the RMS error of the residuals. So we calculate the residuals. So we calculate the mode, and then we compare them with the true distance, which is known because this is a fake data, so we know everything. But we calculate relative to the true distance. Right. So this is for the uniform distance with the limiting distance 100 kiloparsec on average. Yeah, it's very bad. So it's going to be highly biased, even when the observed if the true relative error is more than 20%, it already goes really bad. And here, if we use exponential space density, so the bias is very low, and the uncertainty estimate is not bad. Standard deviation of the bias. Sorry, the standard deviation of the residual. No, it's not bad. But we can see here that when the star is poorly measured, then it starts to get a really high bias, because it tends to become prior dominated at this area. So then we get the wrong estimate, and that's why it gets really biased. Now the exponential space density, on the other hand, well, here it's highly biased, but for large distance, it's actually less biased. And so there is some work to it to use highly informative prior. But this also reflects the problem that if we use the wrong prior and we have bad data, then it's going to be highly biased towards the prior. But as you can see, it's not really bad. Actually, it performs in this area. It performs better than the exponential space density, which is also informative, but not as informative as the Milky Way prior. Right. So that's the RMS error. The Milky Way performs worse than the exponential space density, but obviously both of them are much better than if you just flip the parallax on the left. So don't do that. This is the RMS error in various distance. As you can see, it's more or less the same, except anywhere towards the galactic center, because this is the area where it's very much informative. So yeah, don't flip the parallax. It does not work for negative parallax and also for poor parallax measurements. And any prior is actually fine for anything less than 0.1%. But for we want to see if you want to have a nice transition from data dominated to prior dominated, just use a informative prior. It'll be good. So this is going to be if you're feeling like it, I've set up assignment that you can try to see what the posterior looks like. So how do we do better? Yeah. So if we have more information, by all means, include them in the inference. So I will see how tomorrow how that will work in practice. So that's everything. So thank you. And we still have some time for questions.
Okay, thank you very much, Dr. Tri Laksmana. That is the lecture, your lecture for today. Is there any questions from participants? Please, you can raise your hand or type in the chat room. Any question? Okay. If there is no question, maybe I'll ask something.
Yeah. Yes, please.
I think there is many different results when people try to measure the Hubble constants. Yeah, different different measurement can give different results. Yeah, it is very critical in the theory of cosmology.
Yeah, it's called a Hubble gap.
How do you think this method can help to select which one is have a higher probability to be true, or which one is a lower probability? Can this method help?
Well, yeah, actually, it has been used in cosmology. This Bayesian inference is the bread and butter of cosmological investigations. So the problem is not in the method. They all use the same method. Both who observe supernova and those who observe the CMB. They both use the same Bayesian inference, same package sometimes. But the problem is it lies in the assumption and the data that it takes and the approach. So that's something that we cannot solve today. The people who observe supernova or Cepheids, they are more driven by data, by what we observe. I observe supernova at this redshift. Okay, the distance is this, and the Hubble expansion is then this. So the model is used to inform the observations. Now I think the problem with this, I think this in CMB it's a little bit more like they try to start from the Big Bang and then put a little bit more assumptions than what we can actually observe. Okay, I assume a universe model and this atomic parameters, etc. And then this is what I observe with the CMB. So we have different data set, we have different approach, and that's why we have different results. Either both are wrong, somebody screw up. It's non-conclusive at this point. So, but everybody agrees we have to take more data. So that's why we built another telescope to observe more supernova. That's how it is.
Okay, thank you for your answer. There is a question in the chat room. Yeah, from Obi. Do you want to say your question by yourself, Obi, please?
Sure. Sorry. Good morning, Prof. So greeting from Singapore. So I was actually trying to run your code that you share with us on the IPython notebooks with the collab. Yeah. So
Okay.
When I was trying to run the Nataya something estimator, I encountered that for some scale length, it prompted me that it's actually having division by zero error. So is it because like something in the code is wrong, or is it just something to be expected from the scale length?
Yeah, and it's something that you can expect from the scale length. You see, because you usually get division by zero error because we are using kernels with compact support. So it's only non-zero in a certain range, but then outside the range it's zeros. So if you use a scaling that's very short, then it cannot find data inside the bandwidth, right? So you get zero data, then the kernels return zero. And because Nadaraya Watson estimator is a weighted kernel, you have to divide by the sum of the kernels. When the scaling is very short for all data, then the sum of the kernel is zero. That's why you get division by zero errors. So don't try kernels that are too short. You have to look at you have to look at what is the minimum distance between two data points. That's the minimum size of bandwidth that you have to pick. So it's quite normal. If you want to avoid that, use kernels with infinite support. So, I mean, kernels that are non-zero everywhere, like the Gaussian or sigmoid, etc.
Actually, I have slightly a little bit one short more question, which is that when I also run the cross validation code, so I didn't activate the part where you have the preset seed. So every run you have a different seed, and maybe because it is not the exact function, so every time I run the cross validation, they tell me a different order, like different best order. Then sometimes I run into like order 4 is good, and then sometimes order 11 and so on. So you know, when we actually doing experiment, we might not know the exact function. So when we might encounter this kind of issue, right, where like each run may give us a slightly different what do you call it, best model. So how do we perhaps select which one is the best?
It totally depends on the data, right? So in real life, we cannot rerun. We cannot get new data by changing the seed, right? You only have a single set of data.
But my concern is that when, for example, we do leave one out, then each one
so
of them will have. Sorry.
So there is no. If somehow we can repeat, if we can go back in time and repeat the experiment and get new set of data, then yeah. So the cross validation, you'll get different orders. That will totally depend on what kind of data you get, and especially the noise. Yeah, because I think we set the noise to quite high. So if we lower the noise, you'll probably get consistent order of polynomial each time. We rerun the data with different seeds. You get new data set. That tells us that the data is pretty good. All right, so that's why you get consistent orders each time.
Okay, sure.
So yeah, cross validation. It just basically don't care about what's going on in the model. It just care about making predictions. If that's all you care, then by all means use cross validation.
Sure. Thanks, Prof. Yeah.
All right.
That helps.
I'm not a professor, so
Okay.
No title, please.
Thank you for the answer. So, is there any other questions?
Yeah, especially about Bayesian inference. Or if everything's crystal clear, then you can ask anything else.
We still have about 6 minutes for a question and answer. If you want to say, or if you want to add something. Dr. Laksmana?
No, I think that's
all.
that's everything that I can say. I mean, if there's no questions, we can probably have an early break. We can go to sleep.
Yeah, it seems this method is now increasingly usable for the astronomical research. Yeah. So
yeah, I hope this is useful for all of you who are not familiar with the Bayesian method. I think the message is from both me and Professor Feigelson is quite clear. Think about the prior. If you want to use Bayesian method, understand why we get these results.
Yeah.
What happened if we change prior? So the best prior will totally depend on what sort of data do we have. So we have to understand the characteristics. We have to characterize the data, and we also have to think about what sort of scientific model that can explain the data. So sometimes the best model is not the one that is highly informative, like the one that I show you. We try to put everything in. We use the Milky Way mesh model. We have luminosity function. We have this extinction model. Turns out it's not better than it's not too much better than the one that's actually quite flexible, the exponentially decreasing space density. So it's a beautiful model. It's a simple, and it actually works very well. And it's also somewhat informative. However, we can see also it has some certain limitations in area. So understanding this kind of things, I think, and being able to express that in our report is, I think it's going to be very good.
So it seems the Bayesian method is developed in the same time with the increasing data exponentially. Is there any correlation between the big data and the development of Bayesian?
Yes, in some degrees it is. When we have computers, because Bayes theorem, to get anywhere, we need a lot of computational power. There's just nothing like that a long time ago.
Yeah.
As we have seen, we try to use conjugate prior that makes things easier with when we are just using pen and paper or simple computers. But now we don't care about it. We use now because it turns out that to make Bayesian methods become powerful, we need a lot of numerical method like Markov chain, Monte Carlo, and all of that, and that can only be done with the help of computers. So that's
okay.
So that's why it become really, really popular now, because
so we need also the other method, to help with.
But in terms of machine learning, it's not only Bayesian methods that's actually become popular. Actually, in machine learning, what is also popular is a lot of methods from linear algebra. So a lot of methods. It's actually something that we learned in university when we took linear algebra class. I was reading a book about kernels and stuff. I said, "This is I learned this in university." So too bad I didn't pass very well at the time. So. Otherwise, I might be.
Okay.
So so don't be afraid of linear algebra. If you're very good at linear algebra, it's machine learning. It's probably not going to be very difficult.
Okay.
Factors and matrix. Okay.
Okay.
So
thank you very much.
Question?
So it seems there is no more question.